This lesson's on significant digits and rounding. You'll be able to understand and explain how significant digits communicate the level of precision in our measurements. You'll be able to recognize the number of significant digits in a value and round a value to a given number of significant digits. And you'll be able to apply rules for significant digits when you're doing mathematical operations. Let's start by looking at an example. Imagine that we're measuring the length of an iron nail. Here are 4 possible ways we could report our measurement. We can ask which of these reports implies the most uncertainty and which implies the most precision or exactness in our measurement. Well, the first one looks like it was probably measured using a standard classroom ruler, something that might look like this, with a 3 centimeter mark and a 4 centimeter mark, maybe no marks at all in between. And perhaps the nail came to right about there. And so we eyeballed it and we said, that looks to me to be about 3.4 centimeters. In contrast, we wouldn't report this measurement from our classroom ruler because these are all guesses. We really don't have any way of knowing whether it's 3.4, etc., 1, 3.4, etc., 2, or maybe a bit less than that. So this is actually conveying a lot more exactness than we can capture using this ruler. The first one shows the most uncertainty, whereas the last one is demonstrating the most precision or exactness. And again, whether that exactness, that precision is reasonable depends on a few different things. Well, it's going to depend on the nature of our measurement device. If we're just using this classroom ruler, reporting all those zeros is not going to be reasonable, but maybe we have some sort of optical laser device that captures a lot more information. It's going to depend on how we use it. It might also depend on something to do with the nail itself. For example, the ends of nails are not perfectly flat, and so it might make a difference where we measure the nail's length too. So the variability of the object as well. And there might be other factors too. Now, we call digits that are telling us something about the precision of our measurement significant digits or significant figures. And you'll see that abbreviated as sig figs or SF. And we want to avoid implying more precision than is reasonable. So we need to quote things to an appropriate number of significant figures. For example, we wouldn't want to use, again, this ruler and report that measurement. We also need to be careful that we don't inflate the significant figures artificially when doing calculations. For example, just by writing down whatever our calculator spits out without thinking about it. Let's understand what digits are significant and what aren't. Here are rules for whether something is a significant figure. First of all, anything that's not a 0 counts as a significant figure. Zeros are more difficult. You have to look and see if there's a decimal in the number. If there's a decimal in the number, then end zeros become significant. If there is no decimal in the number, then end zeros are not significant. Leading zeros are never significant, and middle zeros are always significant. Okay. It gets much easier when we look at some examples. So here there are no zeros, only non-zero numbers, so that is 2 significant figures. Here there are 2 non-zero numbers, leading zeros are not significant, so again, 2 significant figures. Here there are 2 non-zero numbers and 2 zeros at the end, so we need to look, is there a decimal? And there is, so these zeros are significant, and that's 4 significant figures. Middle zero is always significant, so that's 3 significant figures. These are middle zeros. Doesn't actually even matter that there's a decimal, but there is, so that's 4 significant figures. End zeros, like this one, are only significant if there's a decimal in the number, like up here. In this case, there's no decimal in the number, so this is only 2 significant figures. However, when we put a decimal and then another 0 after it, now we have many more. In fact, we have 4 significant digits. Notice that you could think about this as being this same measurement, but with a more precise measuring device, like we saw above. This 530 might actually have been a 529 or a 531 that we just couldn't be too sure about and rounded to 530, so it has fewer significant digits. We've skipped from 2 to 4 significant digits. What if you wanted to have 3 significant digits for this measurement? Well, you could put a decimal place there. That decimal place, by our rules, turns this 0 now into a significant figure. And so we have 3 significant figures in this case. But this point is pretty hard to see, and so you might mistake that for 530 with only 2 significant digits. So a safer way of doing it is to write it in scientific notation. 5.30, that clearly has 3 significant digits because this 0 is significant because of the decimal, and so we have 3 significant digits. Having the right number of sig figs often means you're going to have to round your final answer. So let's take a few moments to talk about rounding. Well, what are you really doing when you're rounding? You're deciding on the last place value that you're going to keep, and then you're changing everything else after that. You're either making it 0 if it's before a decimal point, or you're just dropping it off completely if it's after a decimal point. For example, if we were to round 123 to the nearest 10, this is all before a decimal point, you can imagine the point being there, then that 3 becomes a 0. In contrast, if I want to round 1.23 to the nearest 10th, I don't write 1.20 because that's the same number of decimal places. I write 1.2. I just drop that off completely. So we're going to need to look one place to the right from the last decimal place that we keep in order to figure out how to round. In other words, I needed to look at this place here in each of these cases. So to review those rules that you probably know from before and to add a little twist, if the number that you're looking at is less than 5, you round down. For example, rounding 3.52 to the nearest 10th, I look at that 2 and it's below 5, so I round down to 3.5. If I were to round 772 to the nearest 100, I look at this 7, and because it's greater than 5, I round up to 800. What about if that digit that I'm looking at is a 5? Well, you might be used to the rule where you always round it up that you might have come across in math. In physics, actually, we have a slightly different rule, and that's that we always round to the even digit. For example, if I want to round to the nearest 100th, meaning I want to have this as my final decimal place, I look here and I have that as a 5, I'm going to round to the even digit, so 1.02, because 2 is even, not 1.03. In contrast, if it were 1.055 and I want to round to the nearest 100th, I look at this, get a 5, now I round to the nearest even, so not 1.05, but 1.06. So why do we have this different rule? Because physics is an experimental science, and if we were always rounding up whenever we had a 5 here, that would slightly bias our results because we would always be making things bigger, not sometimes making them bigger and sometimes making them smaller. So that's why the rule is a bit different in physics. Be careful not to round twice. That's a common error. For example, if I were to round 3.749 to the nearest 10th, I want to round to this decimal place, so I look here. That's a 4, so I round it down. The correct answer is 3.7. What people sometimes do is they see this, they realize it's close to a 5, they mentally round this to a 5, and then they round again, and they get the wrong answer. So just be a bit cautious about that. Let's talk about multiplying and dividing numbers. When you're multiplying or dividing numbers, you want to give your answer to the least number of sig figs in any of the numbers in the question. For example, if I multiply 1.1 times 3.002 meters, then my calculator gives me 3.3022 meters squared, but that's not what I'm going to write down as my final answer. I'm going to write down instead 3.3 meters squared because this has two significant figures, and so I round my answer to that. Similarly, if I were to divide 5.2 kilograms by 0.253 meters cubed, although my calculator gives me something that looks like 20.55335, etc. kilograms per meter cubed, what I'm going to write instead is that rounded to two significant figures, so actually just 21 kilograms per meters cubed. Again, multiplying or dividing, give your answer to the least number of sig figs in the question. Adding or subtracting has a different rule. We need to give our answer to the least number of decimal places. So you don't actually need to know anything about the lesson preceding this for adding and subtracting. You just look at the least number of decimal places. In this case, if I were to add these two, that's just one decimal place. So my answer is going to be 220.8 centimeters. Not the 220.753 centimeters that I get. If I add them exactly, I round to this decimal place here. In more complicated multi-step problems, a good general approach is to take a look at all of the numbers given to you in the question and report your answer to the lowest number of significant digits given in the question. In order to do that, you're going to want to carry at least one more digit during all the intermediate steps that you need in your answer. That way you can round at the end. Okay, that's an introduction or a review of significant figures and rounding.